Okay, we prove something like this. If R is not zero divisor in R, then for any module, higher Tor from M to R modulo R is 0. Tor, the first Tor is R torsion, the zero Tor is M modulo MR. And for Ext, the same thing. Higher X are 0 from R modulo R to something. 0 Ext is R torsion, and the first Ext is M modulo R. Now, okay, let's forget this for a second. About Tor, about flat models. Okay, at first, flat model is such model which preserves exactness. There's a product which it preserves exactness. Okay, the first one. If R has no zero divisors, then flat implies torsion-free. Yes. No, it's because of this equality. Because for any element in your ring, you can consider cyclic module, the first Tor, and if M is flat, it must be 0, and this is R torsion. So there is no torsion in general. If it has no zero divisor, no, it's more or less sensible assumption. Okay. It's not true in general. For example, what exercise? Check that we consider just polynomial ring in two variables. And consider ideal generated by X and Y. It's any polynomial without constant term. This is module. This module is torsion-free, but it's not flat. Check that it's not flat. It's torsion-free, no, by obvious reason. Okay, it's torsion-free, but not flat. So, of course, it's not true in general, even for such not very scary ring. Okay. Okay. Now let's prove something about flat modules. For example, let's check the first thing. For example, for abelian groups. Okay. For abelian groups, it's true. In general, maybe today we will prove that it's true for principal ideal domains. So it's true for polynomials in one variable. But it's two variable. It's not. This ideal is not principal, so it's not true. Okay. But let's start with this thing. Q is flat as abelian group, flat over Z. Did you check this? Maybe not. But Q is flat.
Q is flat over Z. No, I haven't checked this.
Okay, let's check. We can check this. No, this is checked more or less directly. For example, what we need to check that if we have inclusion of abelian groups, then after tensor product with Q, it's also injection. So we need to understand what the tensor product with Q is. No, the first lemma that tensor product with Q, it's so-called localization or rationalization of abelian group. It's isomorphic to so-called, I don't know, A localized at 0. Sometimes it's denoted by this. It's by definition this thing. It's by definition set of fractions A over N, where A is from A, N is from Z without 0. Modular relation A equivalent to Bm if what? Now if you have cross product Am minus Bn, but maybe not 0, but it's torsion after multiplication by some element, by some other integer k, it's 0. You can check that this is equivalent relation. If you don't use this k, it's not equivalent relation. If you use k, it's because maybe you have torsion in A. If you use this k, it's equivalent relation. It's some set, and in fact, this is abelian group. You have abelian group structure on classes. No, oh sorry, it's defined by our known formula, am plus bn modulo mn. Then you can check that this is in fact abelian group with this 0, for example. Okay, this is equals to any other. Okay. Okay, let's check that this is isomorphic abelian groups. So if you check that on the right it's indeed abelian group, then let's construct. Oh, isomorphisms are very direct. No, in fact, proof that isomorphic A tensor Mn goes to Amn. Okay. Now maybe you need to check that this is correctly defined, but it's correctly defined. The sum. No, you need to check that sum of these elements goes to sum of these elements, but it's from this usual rule of addition. You can check that, for example, if A plus B tensor product goes to sum. No, goes to no, it's equal to A Mn plus B Mn. No, it's obvious that they goes to the same element, yes. But also it's true that if you have A tensor product Mn plus KL, and then usual rule, then it goes to think that it's the same thing by this rule, okay? Okay? Because addition is the same as we expect on fractions, okay? Now you can check that this is correctly defined. Correctly defined, this means that, no, because tensor product is not just these things, it's these things modular relations. If I have sum here or sum here, then it's sum of tensors. And you need to check that the sums goes to sum, okay? Sum in sense sum, not sum. Okay. What, for example, okay, you have this thing, it's equal to A Mn tensor plus A tensor KL. This goes to A. No, this equal to, yes, A ML plus KN NL. So this goes to A ML plus KN NL. This goes to sum A Mn plus A KL. Now this is the same thing by this rule, okay? Okay? So this is correctly defined homomorphism of abelian groups, and I have inverse one. If I have A n, it goes to A tensor 1n. And again, you can check that this relation holds in tensor product, so it's correctly defined homomorphism. And if you check this, then they're inverse to each other. So it's isomorphism. Okay. No, it's a little bit more understandable description of tensor product with Q. It's just fractions. Modulo this relation. Okay. Now let's just prove. Now it's more or less, in this description, it's more or less obvious that if I have inclusion of groups I, then I consider this tensor product, or maybe it's not inclusion, I don't know. It's isomorphic to localization, fractions. This map. How this map acts? No, it just sends an to ian. So we need to check that this map is inclusion. Okay. By definition of my relation, yes, this is exercise to check that it's all correct, and I will ask you on the exam why it's correct, of course. No, it's not. It's very easy. If ian is 0, 0 is 0, 1. By my relation, this means that ai on 1 is 0, and some k I a is 0. It's by definition my relation.
Wait, what?
my relation, I,
No.
yes.
Why are we considering
K,
AI divided by N?
it's image. If you check, then on localization, this acts by in this way.
Okay. We took some element.
So if I need to check that it's injective, so let's it's in kernel. This is 0 in my localization group. So this equivalent to this. This is I, K, A. And because I is injective itself, it's equivalent to say that K, A is 0 in A. But this equivalent to say that A, An is 0 in localization of A. So my element is itself 0 in localization. Maybe it's not 0, maybe A is not 0, but it means that A is in torsion. Okay, that's end of the proof. And also, in fact, we check that, no, in the similar manner, we check that the natural map from A to localization to A tensor Q. No, it's induced by this inclusion, yes? ZQ, then after tensor base A, we include this thing. A to A tensor 1, or A1, yes. Its kernel is exactly torsion. Yes, its kernel is exactly torsion. Torsion. Okay, now we proved that Q is flat. In fact, Q is flat. Now let's prove the following thing. That A is a abelian group. A is flat if and only if A is torsion-free. We know that abelian group is projective if and only if it's free. It's injective if and only if it's divisible. And now I claim that it's flat if and only if it's torsion-free. So for abelian groups, we know all these classes of abelian groups. Now, for example, Q is flat, but not projective. It's not free. Q modulo Z, it's injective, but also it contains only of torsion, so it's not flat, for example. Okay. I want to give you three different proofs of this fact, because all these proofs are поучительные. No, the first proof, I think we have already obtained, because if A is torsion, we have already seen that Z is without zero divisor, so if it's flat, then it's torsion-free. Okay, it's always true for any ring without zero divisors in general. So we only need to check this direction. If it's torsion-free, then it's flat. If it's torsion-free, then we see that A embedded to its rationalization. We have inclusion A to A tensor Q. Okay. A tensor Q is flat. Why? Because it's Q vector space. It's vector space over rationals. So it's direct sum of some copies of Q. It's isomorphic to direct sum of Q. Q is flat and direct sum of flat modulus is flat because Tor of direct sum is direct sum of Tor. So if it's 0, then if all of the 0, then it's 0. Okay? So in fact, from this we obtain that any direct sum of Q, any Q vector space is flat, and so any rationalization is flat. Okay? Because tensor product with Q is Q vector space. You can multiply by rationals from the right, for example. Okay? It's an extension of scalars to Q. Okay? So we need to check that any abelian subgroup of flat abelian group is flat. In general, it's not true that submodulo of flat module is flat. But in this situation, it's true. Let's check this. Okay. I have inclusion. Let's consider short sequences have some quotient. Let's consider a long sequence in Tor. Tor with something. Yes. Ну вот и все.
Why are we starting from one?
Because it's abelian groups. We have no Tor second and for all. Yes, you're right that in general we have Tor second with Km, and we absolutely don't know what is it in general. We don't know what it, because it's some quotient. We don't know what it. But for abelian groups, we know that all higher Tors are 0. So we have no here, and it's the end. So we have 0 here, and this is also 0 because it's flat. So it's 0. Okay. It's between two zeros in short in exact sequence.
No, wait a bit. What about K?
No, in general we have K Tor for K second for K here. It's 0.
No, not second. First.
No, we have Tor 1 for K here.
Okay.
It's kernel of this inclusion after tensor with M. Maybe it's not 0. I don't know. But here there is no K. In general, K is here, but for abelian groups, okay. It's the end. So we obtain that any subgroup of flat abelian group is flat, and any torsion-free abelian group is subgroup of its rationalization. And if we know that Q is flat, then we obtain that A is flat. Okay.
What's the problem in general?
In general, we have Tor of this thing of this sort. We don't know what is it.
Yes. Okay, you're right.
So I have that it's surjection of this, but I know that this is 0. And in general, it's not true. In general, it's not true. I give you some exercise about this. Okay. It's the first proof. The second proof, a little bit fun, but it can be okay. Let's see more accurately on this proof and try to generalize this. In fact, this sort of argument works in this situation. It works for any localization. If you have for simplicity, let R is a commutative ring. No, it's not important. In fact, I think if R is commutative, if you have some multiplicative system, it's some subset which closed under multiplication. Then you can consider inversion of these elements, and consider for any module you can consider such thing is just the same fractions ms without 0. F is not 0. Modular same relation m s n s prime m s prime minus n s some s prime prime is 0, and with the same rule of addition.
Once again, S is
it's some subset closed under multiplication. And then I can define this. And this will be a module. If R is commutative, it's a module. It's R module. No, in fact, it's tensor product of you can localize your invert your elements in R itself, and then consider tensor product with M. It's the same thing. So you only need to consider fractions of this form in R itself. And this argument, in fact, works, for example, to say that that localization is exact. So, for example, two exercises. That if I have short sequence of modules, then after localization, it's also short sequence of modules. It's generalization that tensor product with Q is localization of all non-zero elements. It's exact functor. In general, localization is always exact functor. No, and in general, for example, for any R is R is commutative without zero divisors, then if you invert all elements R or all non-zero elements of R, then it's so-called quotient field. It's field of fractions. It's R model, and this R model is always flat. It's flat. No, this is corollary of this general fact that localization is exact. So that's the product with this thing. So in fact, these models are always flat. Any localized models are always flat. This R model is always flat. It's R module. They always flat. For example, For example, not only Q, but for example, if you invert 2, it's also flat. No, we know that it has no torsion, but in general, such things always flat over general commutative rings, something like this. So it's general fact. Okay. All these modules are flat. In general, if you invert all elements, you obtain field, and this field is R module. As R module, it's flat. Okay, no, you can check this general fact. It's exercise. Check these definitions, all these definitions, and obtain this result. Okay, it's general view on the first proof. The second proof, which has even more crucial generalization. But maybe it's not very obvious proof. No, okay, let's start. The second proof that torsion-free abelian group is flat. It's not obvious error, yes. It's the following observation, the crucial here. If you consider any abelian group or any module over any ring is the union of finitely generated submodules. It's the union of finitely generated submodules. Finitely generated submodules. Do you agree?
Yes.
No, because any element contains a submodule generated by itself. Okay. So any abelian group is union of finitely generated abelian groups. If A is torsion-free, then it's union of finitely generated torsion-free abelian groups. And finitely generated torsion-free abelian groups, it's what groups? It's free abelian groups, because finitely generated abelian group, it's torsion and free part. So if it's torsion-free abelian group, and this is finitely generated, then it's free. So it's union of free subgroups, all free subgroups. For example, Q is union of, for example, these subgroups, where you invert one of elements. It's all subgroups, it's union, it's Q. For example, all of this group is free. It's free group, in fact. So here is not, it's not very hard. Think that it's flat, it's free. It's generated by 1/2, but okay. Okay. And now we obtain that this is flat. It's union of flat. In fact, it's general fact that if some model is union of flat model, then it's flat. But we will not check this fact. But in fact, I think maybe even it will follows from this argument. Okay, let's give me an argument. Okay, I have some inclusion again. Sorry, A is my group, so I have inclusion B to C. Yes. B to C inclusion, and I have tensor product A tensor B, A tensor C. I need to check that if it was inclusion, then it's also inclusion. Okay. Now, okay, consider some element from here, x, which goes to 0. which goes to 0. This element contained in some okay, this element is the sum of AI tensor BI. And I consider finely generated free subgroup which contains all this AI. Okay? All this AI lies in one free subgroup in A.
What's again? Why is it true?
No, it's a finite number of elements of I. They lies in finely generated subgroup generated by them. It's free subgroup. This means that if I consider this Zn and this inclusion, I have some Zn inclusion to A, such that after tensor with B, I have some elements here which goes to X. No, these elements tensor this Bi. And also I have Zn tensor C. Okay. Zn is flat because it's free. So in fact, this is inclusion. No, it's not plays a role now, but after some seconds. Okay. But okay, it goes to it's here. It goes to X and then to 0. So if it goes to Z, then Z goes to 0. So by commutativity of the square. What does it mean that Z goes to 0? What does it mean that something is 0 in tensor product? This means that image of Z, that image of Z, Z is some, okay, maybe by the same notation, it's AI tensor BI, and this is the same thing, it's AI tensor BI, where I consider BI from C and AI from Zn. And this is also the same thing, and this tensor product is 0. This means that
Not BI may be.
No, it's because A to B is inclusion, so I can identify elements from A. Sorry, B to C. B to C is inclusion, so I can identify elements from B as elements to C. Okay. No. Okay. Maybe. Okay. Here. Okay. There it's I, B, I. Sorry for I. What does it mean that some element is 0 in tensor product? It means that it's sum of some relations, because tensor product is it's free group generated by these elements, modular relations. The same relations, distributivity, okay? So it's sum of relations in this abelian group. These relations have form some sums of some tensors, A, C, A, C, A, C. I consider all A parts and consider finely generated subgroup generated all these parts. So I have, in fact, with these relations, I have another Zn tensor C, such that this relation is the image of these elements and the same relations of this group. What I want to obtain. And the end, in fact, of argument. So what I obtain, maybe I have this. I have B, Z, N, yes, B, A. У меня просто другие обозначения тут в листочек. Сейчас A, B, A, C, Z, N, C. And also I can consider finely generated subgroup which contains relations and also contains this A. So it's
So we understood that the sum of AI tensor I of BI is sum of relations. So then we formally take those relations. Yes.
Yes, it's relations of this form. It's something like A, B plus B prime minus A prime B minus A prime B prime. And I consider, for example, here I consider A prime and all others. And generate by them one finely generated subgroup by them and by this element. So in fact, I have this my bigger group. I have inclusion Zn to Zn capital. And so this inclusion here triangles And what I obtain? I have x goes to 0, y goes to x, y goes to z, z goes to 0. And I know that z goes to z prime here. And because these relations already holds here, z prime is 0 in this group. This is 0, okay? No, because z is equals to 0 in this group, and all my relations already holds in this group. So in fact, z goes to this bigger sum group to 0 in this, okay? No, I have inclusions to A, and after tensor with C, z goes to 0 in this tensor product. But I know that in fact it goes to 0 already in this tensor product. It's what's my claim. All my relations already hold in this smaller tensor product. It's what I want. It's why I consider these relations. If I already know, I know that this equality holds for free abelian groups. It's just a formal equality. It's just if you consider just formal sums of tensor products, it's equals by trivial reasons. It equals strictly as free elements. This tensor product is equals as formal sum to sum of relations. And so if it's true, if I already have all these elements in my subgroup and any element of C, then I already have this strict equality already in this tensor product.
Can you repeat everything once again?
No, tensor product, A tensor C. Oh, it's free abelian group generated by these elements, modular relations.
Yes.
So if I have some element, A tensor Ci, it's 0 in this tensor product. This means that in this free abelian group, it's not 0, it's sum of relations. And if I consider, and these relations, it's some tensor product with some coefficients of some A alpha, C alpha. If I consider this A alpha, if they, and AI, and I consider subgroup of A generated by AI and A alpha, then in fact, this formal equality holds not in this group, but in this subgroup. Because I consider just this generated by all these things, because all these elements lies in this subgroup. This lies in this subgroup, so its element in fact is of this free group. And relations also hold because it's the same relations. It's tensor product relations.
Okay.
No, you can meditate over this maybe.
No, I understand.
Yes, okay. So I have this commutative diagram. If z goes to 0 here, in fact, it goes to 0 here. And this is what I need because I want to need that x is 0, so I want to need that y is 0. But this inclusion is injective because Zn is flat. Yes, because B to C is inclusion, so after tensor product with Z, it's 0. So I only need to check that this thing is 0. Okay?
Why is it commutative?
No, because it's all induced homomorphisms by inclusions of the first variable or inclusions of second variable. No, you can check. That's all. Of course, they are commutative.
Because
No, these maps and these maps induced. No, these maps horizontal maps induced by inclusions on the second variable B to C. The vertical maps and these maps inclusions on this first variable Zn to greater subgroup. These maps also by inclusion. These maps inclusion of Z of this subgroup to A. All horizontal maps inclusion on second variable B to C and all other arrows inclusions of on the first variable of subgroup to some more subgroup Zn to Z capital N, Z capital N to A, or composition of inclusions is inclusion. Okay.
now I see.
So I have Z goes to Z prime. If Y goes to Y prime here, then I also have this map, and it's also induced by inclusion B to C. And this map is injective because Zn capital, here is injective because Zn capital is also flat. So it goes to 0, so Y prime is 0, okay? Because it's induced by inclusion B to C, and Zn is flat. So it's 0 and it goes to x, so x is 0.
Okay.
So So this map is inclusion. We consider any x goes to 0 and prove that x is 0 itself. This argument about, so in fact, this argument say that if you have, no, again, of course, it's not true that if it's a union of flat modules, it's flat. It's true, in fact, if it's no union in some sense that for any submodule there exists maybe greater submodule which is flat. Well, then it's true, for example. What this argument, как это, verbatim works if M is union of modules, they are flat, and no, and for any, for example, I don't know, and for any two of them, there exists greater module of this family, something like this, okay?
Why can't I take M equals to M?
What? Why we need this? No, because we need some elements. These elements maybe lies in some different modules, and we need one greater module which contains all itself. I need that finite number of elements, any finite. Well, in fact, I need that any finitely generated module lies in some module of this sort, okay? Because then this argument works. It's called filtered system of submodules.
Okay.
And so this argument will say that if this is true and this is all flat, then M is flat. Then no, the same argument works. You have only finite numbers of elements to obtain that some element is 0 into the product, and then you can obtain some one module which contains all these relations and all these elements, and then for M is flat. Okay. Here we only use flatness of Zn on this final part of argument. Okay. Okay. For example, if R is PID, principal ideal domain, Z, or polynomials in one variable of a field, then, no, again, for example, this works for family of all finitely generated submodules, then this is true. And if, for example, if you know that any finitely generated flat module, finitely generated torsion-free module is flat, then any torsion-free module is flat. So this argument works that if any finitely generated torsion-free is flat, then any torsion-free is flat. Because any torsion-free module is union of finitely generated submodule, and any submodule torsion-free is torsion-free, and then flat, and then it works. This is true, for example, for principal ideal domains, for Z or for polynomials over T, because for principal ideal domain, any finitely generated, you also have classification as finitely generated groups. Then you have classification of finitely generated modules, and they have free part and torsion part. And in fact, over PID, any finitely generated torsion free is free, and so it's flat. And so over PID, over Z or KT, any torsion free module is flat. Over polynomials in two variables already, it's not true, as I said before, because it's not PID. There exists a torsion-free, not flat model. So it's crucial that it's one variable here. Okay, it's second observation of this sort. And this generalization was something like this. Okay, let's check. In fact, we have some criterion of flatness which relates flatness with injectivity. Recall that if I have M is, for example, right R module, then I can consider M check as its home as abelian groups from M to Q modulo Z. It's left R module from the right R module multiplication M. We obtain left R module structure on this abelian group. It's left R module. And so our third theorem that in fact M is flat if and only if M check is injective. For example, when we constructed injective resolutions, we used these modules. And we proved, no, this is a coextension of scalars, and we proved that it's injective. No, it's injective because R is free, it's flat. So more general fact is this fact. No, and so third proof would be you can directly check that if M is torsion-free abelian group, then this thing is divisible abelian group, so it's injective, and you can check directly the third proof that torsion-free abelian groups are flat. But we need this, I want to check this general fact. Okay. The first one, the first lemma, and the important thing that, in fact, if I have 3 modules, then this sequence is exact in the middle. If and only if the dual modules are exact. It's covariant functor, contravariant, sorry. Exact. Exact. So home to Q modulo Z not just preserves injection. It's because it's injective abelian group. It's obvious. This direction is because it's injective. But not only preserves, but it so-called reflects injections. So if you obtain injection, if you obtain exact sequence, then you have already had exact sequence in the beginning. Okay, from the left to the right, it's because Q and Z injection, injective module. It's because Q modulo Z injective abelian group. It preserves exactness. It's true for any injective abelian group, for example, Q itself. But the opposite direction is not true for Q, for example. If you have no, I don't know, if you have, I don't know, Z2, Z3, yes, 0, 0, 0 map. It's not exact, but after tensor with Q, it's 0, 0, 0, it's exact. Or after home to Q, it's 0, 0, 0, it's exact. So for Q, it's not true. So it's not, injectivity is not enough here. No, okay, it's maybe I can leave you this as an exercise. It's just direct check. It's direct check that if this is exact, then original thing is exact. Okay, let me leave this as an example. Exercise, sorry, as an exercise. Okay, but if we believe in this, it's direct check as you like. Phi, psi, and so on. Huh?
Can you repeat the argument of the right direction I just?
No, Q modulo Z is injective abelian group. So it's home to it preserves the exactness.
Yes.
No, if I have exact, then it's exact. It's home to injective abelian group.
Okay.
But for Q, it's not true that opposite is true. So it's not for opposite direction. You need it's not enough that it's injective group. You need some other arguments. Okay. No, we something like when we check that all divisible groups are injective, we consider when we constructed injective resolutions, we already consider these groups, and we used that it's injective, and for any torsion group you can consider. No, you can check. What hint for this exercise is that this map M check. Okay, hint that for any non-zero element of M, there exists phi from M check such that phi of M is not 0. You can check this and then use this. We already use this when we consider double check and this evaluation, and this is inclusion. This is equivalent to say for any map there exists some phi that is not 0. And we use this to construct injective resolutions. Then this inject to some injective. Okay, but you can check this thing. We have already checked this, in fact, and use this for this direction. It's from this, it's already very easy. Okay. Now then, this theorem is more or less obvious. The second step. Okay, M is flat what does it mean? If and only if for any inclusion k to n, k tensor m to m tensor n is also injective. Injection. Okay. It's equivalent to say that no, this means that if I have this short array sequence, then this sequence is also exact. Now then I can apply my duality, my check for any short array sequence, for any very short array sequence. This dual sequence is exact. No, dual sequence is in opposite direction. So in fact, this map is surjection. Because this is equivalent to this, say, and I. Okay. But what is this? What is something tensor, something check? No, it's home abelian groups from tensor product. No, yes, here over R, over R, over R, over R, over R, over R to Q modulo Z. But we have injunction, yes? We can move this to the right. It's isomorphic home X to, as R modules here already. Home abelian groups Y, Q, Z. So in fact, it's home from X to Y check. The check of tensor product is home from X to Y check. So this is just home n m check, home k n check 0. No, this is just definition of injectivity of m check. For any injection, I obtain surjection on home to it. It's equivalent to say that m check is injective. So we obtain this criterion. For example, because we know some Beer criterion for injectivity, we obtain some criterion for flatness in terms of ideals of your ring. I recall that module is injective if and only if, by definition, if and only if for any two injection of modules, any map to M, it can be extended to big one. But Beer criterion says that you only need to check inclusions of ideals to R itself. From some ideal to R, if you have map from ideal, then it must be extended to R itself. And then M is injective, if it's true for any ideal, It's Beer criterion. So let's apply this criterion to injectivity of this module, again by adjunction.
So this is, you're going to prove the Beer criterion, yes?
What?
You're proving the Beer criterion, yes?
No. I will not prove, and I did not prove Beer criterion. I just say this is true. And now I need to apply this criterion to this situation to obtain the similar criterion for flatness in terms of ideals. No, I want to apply this criterion to injectivity of dual module.
Okay.
So M check is injective if and only if for any ideal, for any map to M check, there exists extension. No, or maybe in home terms, yes, it's just say that it's surjective on home from R to M check, restriction on ideal is surjective. It's injectivity. But again, we have already seen that this thing home to check is the same thing as check of tensor product. So this is R M check. We have already seen right now. And this is isomorphic to J M check. This is surjective. And we have already seen that check preserves and reflects exactness. So surjectivity is the same thing as without check is injectivity. So it's equivalent to say, and this is M, this is J tensor M. This is M, and here map from G M. So it's injective. No, it's natural map which sends J tensor M to JM. And it's going to say that this is injection. But what is the image? No, image is just image of this map is just so-called model JM. It's a model generated by these multiplications. Okay. And so this equivalent to say that this natural map from tensor product to just product is isomorphism. No, it's always surjective. And we say that injectivity of M check is equivalent to say that it's injective. So it's isomorphism. So we obtain that M is flat if and only if for any ideal this natural map is isomorphism on this submodule in M.
Why is it isomorphism?
No, because it's always surjective. It's just image of this map, model generated by these things. And we have criterion why it's if and only if it's injective. No,
We use injectivity.
Injectivity is the criterion, surjectivity is always true. Yes. So criterion is isomorphism on this submodule or injection to M. Okay, what's no, also.
No, this is okay. What it shows us, why is it just?
No, it's criterion. It's Beer criterion for flatness.
We obtained the criterion for flatness.
Yes, and also I can write something like this. What does it mean that this map is injection? What's the kernel of this map in general? I have this map is this map G R R G is short exit sequence, and I apply tensor product with M. I obtain tensor M. This is my map. It's maybe not injective in general. Blah, blah, blah. And what is this? It's Tor1 of this RG M. And this is Tor1 R M. But this is always 0 because R is free, it's flat. So in fact, injectivity of this map is also equivalent to say that this Tor is 0. So in fact, M is flat. No, M is flat if and only if for any module Tor1 is 0. But Beer criterion say that we only need to check cyclic models which obtain cyclic models which obtain as quotient of R itself by some ideal. If and only if Tor1 of cyclic modules are 0 for any ideal. It's crucial simplification. You only need to check not all models, but only cyclic models generated by one element. Obtained as quotient as ring itself by some ideal.
The 1 is 0, why?
Because this is y. This is 0 is y.
0, why?
Because it's R, it's free, it's flat. It's R itself, R over R.
Okay.
So it's nothing here, and we have only, so the kernel is the image of this map. So it's 0 if and only if.
Yeah.
So this is criterion. We only need to check flatness on this cyclic modules generated by one element. Okay. Now, for example, for Z, again, for Z, you only have Z modulo n, Tor, A, it's n torsion. And if all of them are 0, then you obtain that torsion-free group is flat, fourth time. Okay, because all of these things for Z is just Z modulo sum n. And if all of them are 0, it's equivalent to say that A is torsion-free. And we obtain that it's flat. Okay. Now, I want to check the following thing. For some not very bad modules, in fact, flat modules are projectives. The theorem. If M is flat and finitely presented, then M is projective. Finitely presented means that it's finitely generated, and it has finitely generators and finitely relations. So this means what means that M is finitely generated? It means that we have surjection from finitely generated free module to our M. Okay? This means that it's finitely generated. Because if you can choose finitely many generators, it's the same thing as you have choose some surjection from free module. And finitely presented, that means that this kernel is also finitely generated. So in fact, you have surjection Rm, and we have exact sequence of this form. So we can start our free resolution by 2 finitely generated free modules. This is finitely presented. This kernel is a model of relations, and this model of relations is also finitely generated. It's called finitely presented. So I claim that if M is flat and finitely presented, then in fact it's projective. For example, Q is not finitely generated, not finitely presented, and it's flat, but not free. It's not projective. If you consider torsion-free and finitely generated group, then it's always free. This is generalization. So if you consider not very big modules, in fact, any flat model is projective. It's not very hard. No, it's kind of, it's not. It's also one idea, some induction. Consider for n, we have this homomorphism xi n from, I consider hom over R from M to R. It's yes, it's left R module. Oh no, it's a right R module. If I consider left multiplication of M and R, it's module, R module maps. And if I consider also a right R module function on R, this is also right R module, and I consider N. N is left R module. M and N are left R modules. And I have natural map to home. Да. Sorry, maybe. Yes, here. My flat model here, yes. And any other model here from N to M.
What is this mean?
No, I define this. No, if I have some element phi from this home and M, it goes, no, it's equal to, and I need to apply it to some element of N with phi N. Yeah, it's element from R. It's general map. It's map of, no, in general of abelian groups. If R is not commutative, if R is commutative, it's map of R modules. First, Xi iso for just maybe yes, for it's in fact it's general fact. We will not use a flatness of M at these steps. Its isomorphism for N is R. Okay? Because if N is R itself, is just M, and this is also just M, and this is identification. It's general, it's natural isomorphism. From first step, we obtained that if Xi is isomorphic for N1 and for N2, then it's also isomorphic for the direct sum, in fact, because it will be the direct sum of isomorphism. And so this isomorphism for free finitely generated model for N is Rn. Direct sum of these isomorphisms. And so now I obtained that it's isomorphism for finitely presented modules, for finitely presented module N. If N Xi is iso for finitely presented N, by 5 lemma, because I have, no, here if M is flat, because if I have R, or maybe if I have R, M, R, N, N, 0, I no, yes, I obtain, I apply R, home to R, I obtain from the left, yes, home, N, or maybe here, home from N to R, home Rn to R, home Rm to R. I don't know exactness on this place, but I have exactness here and here. And I have not just home to M. Also, home R, N, M, home R, Rn, M, home R, Rm, M. Also not exactly in this place. But now, if M is flat, I also can tensor product the first Ext sequence by M. And it preserves M. In general, it does not preserve injectivity. But if M is flat, it preserves injectivity. So I can consider tensor product of M here. And I have my general xi's. Xi, xi, xi. And if I know that this is isomorphism for free module, this is isomorphism. So by 5 lemma, I have that this is isomorphism. Because it's isomorphism, and here, if you want, isomorphism between zeros. This is 5 lemma. If you have 2 rows of length 5 and 4 sides isomorphism, then the middle term is also isomorphism. So this isomorphism, and from this, I already obtained that. Now I just proved that for finally represented n and flat m, this map is isomorphism. Now if I obtain n is equal to m, it's itself finally represented and flat. What I obtain? If it's at the same time flat and finally represented, then I obtain that home from m r tensor m to home m to m is isomorphism. So I have a preimage of the identity. Something. What does it mean, in fact? What does it mean that I have some sum of phi I tensor mi, which goes to identity. How this works? This means that, in fact, I have, if I consider m, from I from 1 to n, okay? And m goes at first to Rn by this n linear functionals, phi n, phi n, okay? And then it goes to m, which turns standard basis to mi. And composition is exactly this where these things goes. And I know this goes to identity. No, this composition is a reformulation. This is by definition is psi of this composition. In fact, no, because if I want to apply to m, then I apply functionals and then consider, and then any basis goes to mi. No, you can check that this is just a reformulation of action of psi. And if it goes to identity, then this composition is identity. But no, this means that I have free module and submodule, which is and section. So this is direct summand of free module, so it's projective. So this is direct inclusion of direct summand and projection on non-direct summand. So it's projective. Finally generated projective, or it's summand of finally generated. No, it's finally presented by.
Can you repeat? I agree with this diagram. Why is it projective?
Because no, I have its inclusion to free module, and I have a section. It's inclusion of direct summand then.
Okay.
It's identity on M. So it's projective. Okay. There are some rings, Noetherian rings, over which any submodule of finitely, just 1 second. No, yes. There, of Noetherian rings, any submodule of finitely generated model is finitely generated. It's not true in general, but for Noetherian rings, R at Noetherian, if M finitely generated, then any submodule is also finitely generated. And it's equivalent to say that it's true for ideals. If we have ideal in R, then it's finitely generated. Any ideal is finitely generated. No, and we have some other equivalent properties, but in such situation, finitely presented is the same to think that it's finitely generated, because if you have finitely generated module, then kernel is submodule of finitely generated free model, then it's finitely generated, and we also have Rm. So over Noetherian rings, for example, it's Gilbert theorem of Bayes thinks that any polynomial in any variables finitely many, it's Noetherian rings. So for such rings, finitely present and finitely generated is the same thing, and so we have that finitely generated flat is the same thing that is finitely generated projective. And moreover, if I have M, any flat module, it's always union of all finitely generated submodules, all finitely generated submodules. And if it's flat, okay, yes, you say that, so if it's true that it's a union of flat finitely generated submodules, then in fact it's union of flat finitely generated projective module. So as we have seen for Q, it's union of torsion-free, but in fact they're all free modules. And this is true over general rings. Okay. Now I can say that it's union of flat modules, no, okay. So for good rings, not very big rings, for which any ideal is finitely generated. Finitely generated flat is it's the same thing as finitely generated projective. So if your model is not over not so big ring, and it's flat, then it's flat, and projectivity is the same thing in fact. Q is kind of very big for Z. Okay. And I think the last thing, it's what you wanted. It's Ext and extensions. It was about flat models and Tor, and now let me say something about Ext. No, now Tor, it's called Tor because it's related to torsion, as we've seen now. Ext, call Ext because of extensions, and now let me see how it relates to extensions. It's the first relation. Maybe we will obtain some other relations further, but it's the first relation from the definition. Consider two modules. Consider the following set. It's set of extensions of Mn. It's a set of short exact sequences. It's extension of this form. A short exact sequences of this form, modular isomorphism. Two of them are isomorphic if we have two short exact sequences, and isomorphism which identity on N and M. Maybe they exist, but then we identify them. It's set. Maybe it's not obvious that it's set, but it's set. Now we have seen. And so theorem that this set is in natural bijection with Ext1 Mn. No, in fact, you already can notice that if we consider extension of zero length N to M, it's just home. It's Ext0. This is Ext1. And of course, it's also true. It's Yoneda description of Ext groups. If you consider extension of some length, then it will be Ext_k, in fact. It's Yoneda description. But okay, let's check for k is 1. No, I describe some isomorphism, some bijection. We don't know that it's group. In fact, we obtain some group structure on this set. You also can describe this group structure by hand, and maybe it will be the next size. Maybe, I don't know. Okay. Now let me explain bijection. So, what is element of x1, for example? What is element of x1? Element of x1. What does it mean? This means that I consider some free resolution of M. I consider free resolution of M. I need these three parts. It's free modules, so it's R module with basis Ji. It's generators because it goes to some generators of M. The choice of this surjection is choice of generators of M. Then I have kernel, I have some relations, so I have relations. And the second one called CZGs. It's relations between relations, it's CZGs, it's RSK. It's free modules. Now let me write down how differential goes. No, differential here, Ji goes to some generators Mi.
Excuse me, what we are considering when R is free?
Yes. No, we can do this, okay? We can consider free resolution. Okay. Consider some free resolution. All correctness is exercise for you. This map, D1, D2, yes, it's kind of D0, yes, D0. Or maybe, no, it's kind of D minus 1, yes, okay, it's P, okay, D minus 1, okay, D minus 1, SU, it's D0 and D1. And this is maps between free modules, then they are, no, kind of matrices, yes. No, I define them on basis. D0 of Rj is some coefficients rho ij gi. And d1 of sk is some sigma k j k anyway j i then k j rj. Okay, it's the definition. Okay, so, and what's Ext? I need to apply some hom to n from this, from which one? From the first one, from this one. It's F1. So, element X is cohomology class of some xi. Xi is homomorphism from F1 to n. And it must be cycle. So it must be D1, Q1. D1 prime xi is 0, x composition xi day 1. So it's just need to be 0 D1 and then this map to n. It must be 0. Okay? It's cycle. It's representation of so and any element of X is just sum these cycles. Modular boundaries. Modular plus some phi composition with D0. Phi is from F0 to n. I have maybe some elements from here to n, and I can add some composition D0 and then phi. This is boundaries. Modular these things. Okay. Так. Okay, let's we have extension. Let we have extension of this form. Let me define this cycle. We have the first step. It's from extension to cycles. Okay. Choose some resolution. And choose some resolution, some basis, and so on. Okay. I need something like map from this to n with this property. let we have extension. We have, if we have surjection, then we have some chosen generators, mi. This map is pi, this map is I. This is surjection, so I have some pre-images. Say xi's. Okay. Consider these things. Here, rho ji, xi. It's elements of x. It's elements indexed by j. If I apply pi, it goes to rho ji mi. But this thing is rho ji of z minus 1 of gi. This is z minus 1 of rho gi ji. This is d minus 1 of d0 of rj. This is 0. No, this just means that this is basis relations. This is basis relations in our model. I have generators and this relation. This is basis relations. And this is 0 in my model M, okay? So my projection is 0. So this is goes from n. So in fact, this element is from n. No, if you wish that it's I of nj. Nj is unique from n because I is injective. And this is my definition. I have j elements of n, and this is my images of my basis. So I define xi from f1 from three models with basis rj to n, which sends rj to nj. Exercises here that check that this is cycle, that this is xi composition d1 is 0. Check that this is correct, that if I consider another basis or another free resolution, for example, free resolution, then this xi will be differed from by some boundaries. All other choices goes to plus boundary, plus something like phi composition with d0. No, it's because you need to check that if you consider some other generators, for example, and some other bases here, then you really obtain plus boundaries. And if you have another resolution, two resolutions are homotopy equivalences. And so if you apply homotopy equivalence, in fact, it's the same thing as choice as choice of another basis in this sense. So you really need to check that if you choose another basis and another generators, then you obtain plus boundary just. And then because of two free models, free resolutions are homotopy equivalents, this will be enough. In fact, no, you can check this. So it's correctly defined map from extensions to yes, and of course if you have isomorphism here, then you obtain also. No, this is yes. If you have isomorphism, it's more or less obvious that it's kind of maybe I don't know. No, yes, and if you consider some another pre-images here, you have some freedom here. This also plus boundary. No, it's kind of directly checking. It's some directly checkings. Okay, this is correctly defined map in fact. To homology classes of these maps to Ext1. And another direction. How to obtain extension if we have this class, this so-called gluing class, gluing cycle. No, directly it's more or less the same thing. It's more or less direct thing. I can define it. So if we have some x, it's class of some cocycle. I have some gluing cocycle. Again, I have resolution, and I have phi of resolution of m, and I have map from f1 to n such that d1 is 0. How to define extension? It's very easy. You just consider x the following module. I consider n direct sum with some free module with basis in bijection with generators of F0 or in generators of your M itself. No, you have chosen already the resolution, some free resolution again. And no, yes, I have resolution with the same formulas, yes. And I consider quotient modulo. I have this map Xi Rj, it's some element of n, and I consider this relation rho ji ye I. Ei is from this free module. This is some submodulo of this direct sum, and I consider its quotient. In fact, I have projection. No, in fact, yes, I have projection from X to M to M. No, it goes n to 0 and ei to generator mi. And so this is surjection because I obtain all generators. I have surjection here. And you can check that in fact its kernel, it's this n. It's image of natural inclusion. I have not inclusion, natural map from n to x. Yes, and inclusion to the direct sum and then quotient. It's general map n to x. This is, you can check two things. You can check that this is really the kernel of this map, of this projection. And in fact, this map is injection. So this image is in fact isomorphic to n. So this map is injection and this is the kernel. You need to check these two things. So you obtain extension. No, and then more or less obvious that if you have this extension and apply the previous way, previous map, you obtain more or less the same, exactly this xi, if you do all the right choices. In the opposite direction, if you have some xi, if you have some extension and consider some xi and construct this extension from xi, no, it's not very hard to check that this extension is isomorphic to the original extension. So it's opposite bijection. So I obtain this extension. You can check this extension indeed. So it's Ext 1.